Hi, this is Mrs. Vrobel. This is part one of covalent bonding. So, in the previous unit, we talked about ionic bonding, and now we're going to talk about the difference between ionic bonding and covalent bonding, and how do you identify a covalent bond. So, when we're talking about covalent bonding, we're talking about two nuclei that have same attractive force on a pair of electrons. And the nice thing about covalent bonding is they actually share their electrons. And remember, the electrons are negatively charged, and there's two nuclei on either side of those pair of electrons. Now, I don't know if you remember, but we talked about quantum mechanical structures, and we talked about the s orbital. And the s orbital is the shape of a sphere. So we have two overlapping spheres that form this covalent bond. And notice that with this overlapping of these two spheres, we get what we call a covalent bond. Okay, chemists like to get more detailed about what they're talking about, and when we are talking about a covalent bond, we're essentially talking about, oops, sorry. Trying to get my pen going here. Okay, there's an interesting symbol here. It's called a sigma bond. So SIG, for those of you that don't know Greek, sigma bond is essentially you have two electrons and they're right in the middle of two positive nuclei. Now you could have another type of bond where it's instead of s orbitals, we could have a p orbital. So remember those balloons, those lobes, they can overlap and they could form a single bond. So we could have something like this. So with a p orbital, we essentially have two lobes overlapping, and there's two electrons that reside in that overlapping. We also can have a perpendicular set of p orbitals that are overlapping. Now this is specifically called the pi bond. So you know the symbol that you've seen, 3.14. Okay, this is called pi bond. And you need to have p orbitals in order for this to happen, okay? And this is actually found in multiple bonding. So you're going to have more than just a single bond. And then a third type of bond that we could have is what we call an S and P. So we could have a sphere with a p orbital overlapping, and that essentially creates a covalent bond. Okay, now there actually are situations where we can have polar covalent bond. Now before I do that, I just want to show you. This is an electronegativity chart. So notice that wherever you see like that dark fuchsia, that's where the electronegativity is the greatest. And then if it's more of a faded white or gray color, that's lower electronegativity. Now, when you look at the periodic table, notice that like hydrogen is darker in color. And obviously this section in here where a lot of the non-metals reside, that is very dark in color. You do have a slight group of electronegative atoms in the transition metals, but we're actually more concerned with this section and hydrogen. Now let's go back to what is a polar covalent bond. Okay, so what happens is there are some atoms that don't play nice, and they actually kind of hold on to their electrons more than usual. So we call it unequal sharing. Now with this unequal sharing, what happens is you essentially have a partial charge, and this partial charge has an interesting symbol to it. Okay, this is called delta. So this is a delta charge, And if it's a partial positive, you'll see a delta positive. If it's a partial negative, you'll see a delta negative. So if a molecule, which has a covalent bond, has unequal sharing of electrons, we call it having a dipole. Okay, so as I mentioned before, this is a very similar chart that I just showed you. The only difference is it's blue instead of fuchsia. And it is helpful in deciding whether or not you have an electronegative atom. But, I would just notice that if you are talking about atoms that are close together, their electronegativity is not going to be as great. But if they're more than one space apart, we're talking about a greater separation of electronegativity. Okay, here we go. So these are the different types of single bonds that we can see within a covalent bond. So we can have essentially an SS overlap. So when we have an SS overlap, we have a covalent bond there. And notice it has the sigma symbol to it. So these three are sigma bonds. We could also have two pp lobes overlapping. And when they do, they create a single sigma bond. Or we could have the instance where we have an S and a P orbital that overlap, and together they form a sigma bond.